Welcome back, Focus Learners. Okay, so today we are jumping into a really, truly fascinating explainer on exactly how artificial intelligence manages to completely conquer incredibly complex games. You know, when you sit down and watch an AI play a flawless, and I mean flawless game of chess, or just totally dominated Go, it honestly kind of looks like magic, right? But it's not magic, not even close. It is a brilliant, highly structured application of mathematics and some seriously smart algorithmic shortcuts. Because think about the sheer scale of the branching factor in these environments. The very second an AI looks at a game board, the possibilities just explode exponentially with every single move, and then every counter move, and then the counter moves to those. It's a giant, overwhelming web. So how on earth does an AI navigate this massive web of computational possibilities without, completely short-circuiting its processors? Well, that is exactly what we're going to unpack today.
Right, so the central question here, the big puzzle we need to solve is this. How do computers play perfect chess without checking every single move? To really put this into perspective, a standard game of chess has more possible game variations than there are literal atoms in the observable universe. Yeah, just let that sink in for a second. More than the atoms in the universe. So if a computer tried to process a standard time complexity, meaning evaluating every single possible future move all the way down to the endgame, it would take billions of years. Billions. It would completely max out the physical limits of literally the most advanced modern supercomputers we have. Checking every single move simply takes way, way too much time. So how exactly does an AI algorithm know what to do next in a matter of what, seconds? Well, it uses some highly sophisticated shortcuts to basically completely ignore the vast majority of that game tree.
Okay, let's dive into this. We are going to map this out in 4 exact steps. 1. Trimming the game tree. 2. Defining alpha and beta thresholds. 3. Building heuristic evaluation functions. And finally, 4. Overcoming the horizon effect.
All right, so let's kick things off with Section 1, Trimming the Game Tree.
To really understand how an AI plays at this level, we first have to recognize the massive, towering computational hurdle sitting in front of it. The standard baseline algorithm used in game theory is called Minimax. Minimax essentially assumes both players are playing absolutely perfectly. But here's the catch. Minimax evaluates every single option. In computer science, we represent this massive time complexity as O to the power of m. In that formula, b is the branching factor, so the number of choices you have per turn, and m is the maximum depth of the game, or how many terms the game lasts. As we just established with our atoms in the universe analogy, that number gets way too big, way too fast. And that brings us to a real game changer. It's our core principle here. Alpha-beta pruning. This is an algorithm that mathematically discards irrelevant branches of a search tree without altering the final optimal decision at all. Think of it like this. If the AI is searching down a path of possibilities and it mathematically proves that this particular path is completely undeniably worse than a different move it already found earlier, it just stops exploring it. It prunes the remaining child nodes. It essentially says to itself, look, I already have a guaranteed better option sitting right here in my pocket, so I don't even need to waste my time looking at how bad this specific path gets. It literally chops that calculation off right then and there and saves all that precious computation time.
So you might be wondering, how does it actually know when to break out the shears? Let's move to Section 2, Alpha and Beta Thresholds. Okay, so here is how the algorithm keeps track of what to prune. It uses a clever tug-of-war between 2 critical variables, alpha and beta. In these algorithms, we typically call the AI max because obviously it wants to maximize its score and win the game. We call the opponent min because the opponent wants to minimize max's score, essentially making max lose. So alpha represents the highest value, the absolute best choice that max has found so far along its path. It actually starts all the way down at negative infinity because max is constantly looking to push and improve that score upwards. You can think of alpha as max's safety net. It's the guaranteed minimum score max absolutely knows it can force. Beta, on the flip side, represents the lowest value, the best choice found so far for min. It starts at positive infinity because min wants to drag that score down, down, down. Beta is the absolute ceiling. It's the worst-case scenario that the opponent, min, will ever allow max to achieve. So as the algorithm does what we call a depth-first traversal, which just means it dives incredibly deep into one specific sequence of moves before it even bothers looking at the others, it's constantly, continuously updating these 2 values. It keeps alpha and beta right in its back pocket the whole time.
And this leads us to the ultimate trigger, the pruning condition itself. At any point during the search, if alpha becomes greater than or equal to beta, the search below that current node is immediately terminated. Why? Because a mathematical contradiction just occurred. Let's break that down. Imagine Max has found a move that guarantees a score of 10, right? That's our alpha. But then, down a brand new branch we're exploring, we calculate that Min actually has a response that caps Max's score at a measly 5. That's our beta. Well, since Max already knows a perfectly secure way to get a 10, it will absolutely never ever choose this new path where Min can just force it down to a 5. And it works the exact same way in reverse. Min would never allow a path that gives Max some massive advantage when Min already has a much stronger defensive option somewhere else. Because we assume both players are going to play perfectly, the exact moment alpha meets or exceeds beta, that branch is mathematically dead. There's no point in looking further. The computer just stops calculating, pulls out the shears, and prunes it entirely.
And this brings us to a number that perfectly illustrates the sheer, unbelievable power of this technique. The time complexity dramatically drops to O of b to the power of m divided by 2. Now, the efficiency of all this pruning relies entirely on one thing: move ordering. If the AI happens to evaluate all the absolute worst moves first, well, no pruning happens at all. The alpha and beta thresholds just never get tight enough to cross each other. But if the algorithm uses what we call perfect ordering, meaning it evaluates the best, most promising moves first at every single decision point, it sets incredibly strict alpha and beta limits right out of the gate. When that happens, having that time exponent effectively doubles the search depth the computer can reach in the exact same amount of time. It's wild. If a computer could only see 5 moves ahead before, alpha-beta pruning suddenly allows it to see 10 moves ahead. It completely, totally revolutionizes its strategic power, and it does it without needing a single hardware upgrade.
But here's the reality check. Even doubling the depth isn't always enough for the absolute hardest, most complex games out there. Which brings us to Section 3, Heuristic Evaluation Functions.
Right, so here is the next major hurdle the AI runs into. For highly complex games, even with super aggressive alpha-beta pruning, the game tree is still just too vast. The AI simply cannot reach the terminal states. The actual end of the game where a win, loss, or draw is officially finalized. It's just going to run out of time on the clock. So the AI has no choice but to cut the search early. It has to stop looking into the future and instead just take a mathematical snapshot of the board at that exact moment to try and estimate who is winning. To pull this off, it applies what we call a heuristic evaluation function. Basically, this function maps the entire complex game state down to a single real number that represents its goodness from Max's perspective. Now, designing a truly good evaluation function requires 2 absolutely crucial things. First, agreement with utility. That simply means it absolutely must rank final outcomes correctly. Wins have to be greater than draws, which have to be greater than losses. Makes sense, right? Second, and honestly, perhaps most importantly, it must be highly, highly efficient to compute. This function is going to be executed millions upon millions of times per single turn. If the math used to estimate the board state is even a little bit too slow, the whole AI just grinds to a halt.
So, how do they make these calculations blindingly fast? Well, programmers typically use linear weighted features. If we take chess as an example, the AI identifies critical features of the board and assigns them specific weights. For instance, a pawn is worth 1, a knight is 3, a rook is 5, and a queen is a massive 9. The AI just rapidly counts up all its pieces, multiplies them by these assigned weights, and adds them all together. Then it subtracts the opponent's score. It also throws in positional features, things like king safety, pawn structure, or who has control of the center of the board, and each of those has their own mathematical weights too. By quickly aggregating all these weighted features together, the AI generates a single float number, let's say something like plus 2.5, and that simple number tells it, okay, I am currently ahead by a small margin. It relies entirely on this rapid-fire estimation to confidently choose its moves when it just can't see all the way to a checkmate.
Okay, so we know the AI has to cut off its search and estimate, but how does it decide exactly when to do that? Let's explore our 4th and final section, overcoming the horizon effect.
Implementing that heuristic search we literally just talked about requires the AI to replace terminal tests, looking for the end of the game, with cutoff tests. The AI needs a very concrete rule to know when to stop expanding nodes. There are basically 2 standard cutoff strategies here. The first is a fixed depth limit. This one is pretty straightforward. The programmer explicitly tells the AI, hey, only search 8 moves deep and then stop and evaluate. That's it. But the second, much more common strategy you'll see in modern AI is called iterative deepening. And this is a frankly brilliant way to manage the turn clock. The AI runs a full, complete search at depth 1. Then it starts completely over from scratch and runs a full search at depth 2. Then depth 3, depth 4, and so on. It just keeps pushing deeper and deeper and deeper until the exact moment its allocated turn time runs out. And when that buzzer sounds, it simply returns the best move it found from the deepest fully completed pass. This is so smart because it ensures the AI always has a mathematically sound move locked and loaded, no matter how much or how little computing time it was actually given.
But here is the catch.
The crucial point is, deciding to cut off a search early creates a massive, glaring blind spot. And in the industry, we call this blind spot the horizon effect. It's a major, major vulnerability. It happens when an inevitable, highly damaging move by the opponent lies just beyond the search horizon, which is the maximum depth the AI is currently allowed to look. Because the AI is relying completely on that heuristic evaluation exactly at that horizon line, it can look at a board state and think, wow, I'm perfectly safe, completely unaware that a devastating trap is springing right outside its peripheral vision.
To really visualize this, imagine a scenario playing out across a simple 3-turn timeline. If the AI's search horizon ends exactly at turn 2, things can go horribly, horribly wrong. Let's say the AI calculates that on turn 3, its incredibly valuable rook is going to be captured by the opponent, and there is absolutely no way to save it. It's a goner. But remember, the AI's vision cuts off at turn 2. So what does the algorithm do? The AI deliberately sacrifices its own bishop on turn 1, literally throws it right into the line of fire. Why? Because the opponent is now forced to spend turn 2 capturing that sacrificed bishop. By making this delay move, the AI successfully pushes the inevitable loss of the rook onto turn 3. And here, right here, is the tragic algorithmic flaw. Because turn 3 is now pushed just past the AI's search horizon, the evaluation function takes its snapshot at the end of turn 2 and says, hey, great news, we only lost a bishop, the rook is totally fine. The algorithm falsely believes it has completely avoided the disaster. It tragically makes these suboptimal stalling moves that actually damage its position even worse overall, just to push a loss past its vision. It's a classic case of outsmarting yourself.
Now, obviously, AI developers couldn't just leave this glaring, fatal flaw in the system. They desperately needed a way to force the AI to look past the immediate chaos, and that ultimate fix is called quiescence search. Quiescence is just a very formal, fancy word for stillness or quiet. To mitigate the horizon effect, the AI is programmed to be just a little bit flexible with its cutoff line. If the search reaches the horizon limit, but the game is currently in a non-quiet state, meaning there are wild, chaotic tactical fluctuations happening right then, like active piece captures, checks, or immediate threats, the AI just straight up refuses to stop searching. It temporarily extends its search beyond the assigned cutoff depth. It will just keep following that chain of captures and counter-captures until the board finally reaches a quiet state, where evaluations are actually stable and no immediate chaotic moves are pending. Only then, once the dust has settled, does it take its snapshot and evaluate. This perfectly, beautifully prevents the AI from being fooled by a stalling sacrifice or some mid-capture illusion.
Which brings us all the way back to the big picture here. As AI algorithms become faster and faster, what incredible real-world problems will be solved by pruning our everyday decision trees? We've spent this explainer looking at game trees, from the strict mathematical cuts of alpha-beta pruning to the lightning-fast estimations of heuristic evaluations. But think about it. Life itself is a complex game tree. Every logistical supply chain moving goods around the globe, every complex medical diagnosis path, every traffic grid routing system in a major city, they are all massive branching trees of decisions. By understanding exactly how an AI effortlessly ignores the mathematically bad choices to focus only on the absolute optimal paths, we aren't just learning how to beat a computer at chess, we are learning how to process incredibly complex real-world variables with unmatched efficiency. So next time you are faced with a million different possibilities, ask yourself, which branches can you prune? Thanks so much for joining me on this deep dive. Keep questioning, keep learning, and I'll see you in the next explainer.